Everyone, we're just gonna wait just a minute to let more people come on in. How many people are in this one? Okay, let's just give it 1 or 2 more minutes to let everyone wake up in the morning. So just before I get started with the material for today, just a sort of broader roadmap, which we'll talk about more at the end. This is going to be the last day of like things that we think that they will expect you to come into Chem 1A knowing. And then next week, we're going to start going into some of the stuff that they're going to cover in the first couple weeks of Chem 1A that's going to come at you pretty fast at the start of the course. So we want to just start giving you background on those materials so that the first couple weeks of Chem 1A go a little bit better. So we'll talk about that a little more at the end of today and the beginning of Monday. But just so you know, this is kind of probably the end of the things that those of you who have taken AP Chem or even Gen Chem have interacted with before. So we'll be kind of changing gears come Monday. So I'm going to go ahead and get started. Today we're going to be talking about acids and bases. So just as a reminder, this is what you would see if you looked at the periodic table for hydrogen. It has 1 proton, 0 neutrons, and then for it to be neutral, that 1 positive proton means that it needs to have 1 negative electron. So we know that it has 1 proton because its atomic number is 1, and then the fact that its mass number is also 1 means that there are no neutrons. So what that means is that if we create an H+ ion, we do that by taking away 1 electron. So now it has 1 proton, 0 neutrons, and 0 electrons. So you should get used to hearing people say, proton and referring to H+ ion. Sometimes they'll be referring to protons within another atom, so that's just kind of a context-dependent thing. But whenever I say, there's a proton in this reaction, that probably means there's an H+ ion. So that'll get a little more clear in a minute, but just wanted to preface that. So there are actually a lot of different definitions of acids and bases. I'm going to use today the one that your textbook that you'll be using for Chem 1A uses. So this defines an acid as a proton donor. So just as an example, HCl is an acid. It has that hydrogen and that chlorine, and chlorine is pretty happy, well, very happy to exist as an anion, so it readily gives up that hydrogen, that proton, and creates H3O+, which is called a hydronium ion. So just to say that again, HCl is an acid because it can easily give up its hydrogen. And a base is the opposite. So a base is a proton acceptor. So NH3, for example, is happy to accept another proton to become NH4+. And by doing so, it's sort of stealing that proton from somewhere. So in this case, I'm writing it as stealing it from water. So what this means is that if I stick HCl in water, it will give up a bunch of its protons and we'll get a really high H3O+ concentration. And if I stick NH3 in water, it will steal the protons from water and we'll get a high OH- concentration. Okay, so as always, please put questions in the chat if you have any. So there's a distinction between strong and weak acids. And by the way, the same distinction applies to bases. I'm just using acids as an example. So strong acids are completely deprotonated in solution. So deprotonated means that they have lost their protons. So if I put HCl in water, every molecule will undergo this reaction. We will have basically no HCl molecules left. They will all split up into their hydrogen and their chloride anions. So what that means is that HCl is a strong acid in water. But if I put acetic acid, CH3COOH, in water, only about 1% of molecules will undergo that same reaction. So I'm showing the reaction here, but only 1% of my CH3COOH molecules will do this. 99% will just keep that last proton. So what that means is that acetic acid is a weak acid in water. It only gives up some of its protons. I want to be really clear that completely deprotonated does not mean that it's given up every hydrogen atom that's on it. So even if CH3COOH was a strong acid, it wouldn't lose those hydrogens that are in the CH3. So there's like an acidic proton, which is the proton that has the potential to be lost. So those protons that are in the CH3 are never really going to get stolen. Those aren't the acidic protons. The acidic proton is the one on the OH. So completely deprotonated would just look like every molecule undergoing that reaction where we end up with the CH3COO- ion. Ask questions if that doesn't make sense. So acetic acid is part of a special class of acids that are called carboxylic acids. So I've drawn the structure of carboxylic acids below, which I think was sort of mentioned briefly in the nomenclature day a few days ago. So that R that's coming off just means like anything. Any, like, that could be, in this case, a CH3, but it could be, you know, CH2, CH3, it could be like anything. And then anything attached to this thing in blue, this carboxylic acid, so a carboxyl group, is called a carboxyl. So all carboxylic acids, which you can tell they have the COOH group at the end, are all weak acids in water. You don't have to memorize that, but just be familiar with this carboxyl group and realize that that hydrogen can be removed to deprotonate our acid. So like I said, bases have a similar definition. So strong bases will be completely protonated in solution. So this is just a table of what things are strong acids and what things are strong bases. Again, don't memorize this, but just be aware that this information is out there and know how to interpret a table like this. So the strong acids all kind of are more self-explanatory. They list each of the things, so HBr, HCl, HI, etc. One thing of note on the strong acids side of things is that H2SO4 actually has the ability to lose both of those protons. So it's a sulfuric acid is a strong acid in removing that first proton. So if I put H2SO4 in water, all of the molecules will lose that first proton to become HSO4 minus. And then it's possible for HSO4 minus to lose that second proton and become SO4 2 minus, but that is a lot less common. So it's a weak acid once it's in its form of HSO4 and it's already lost that first proton. Again, don't memorize that, but just sort of be aware that it's possible for acids to have two acidic protons that they can lose. The strong bases are more in groups. So group 1 hydroxides would mean that first group on the periodic table with OH. And then alkaline earth metal hydroxides, those are one step over in group 2. So it lists them at the bottom here, CaOH2, SrOH2, and BaOH2. And then group 1 and 2 oxides. So that means, hydroxides are OH and oxides are just O. So like Li2O would be a group 1 oxide. Okay. I'm going to pause if there are any questions. Again, don't memorize this, but just understand the difference between strong acids, strong bases, weak bases, sort of generally what that means. Okay, if you have any more questions that come up, please put them in the chat. So pH is a way to measure the acidity or basicity of a solution. So it stands for potential of hydrogen. Some people say it stands for power of hydrogen. Something hydrogen, right? So just as a reminder, this is a reaction I've put on some previous slides. So HCl plus H2O goes to H3O plus Cl minus. So that's what strong acids do. So what that means is that if I put something in water, I can tell how acidic it is by knowing the concentration of H3O plus. So if something is really, really acidic, then it's going to lose all of its protons, and our H3O plus concentration is going to go up a lot. If I had put acetic acid in water, then only 1% of those molecules will lose their proton, and our H3O plus concentration will go up only a little. And so there's a question in the chat about, is HCl a strong acid because it loses all of the protons, and CH3COOH is weak because it only loses one hydrogen? So not exactly. So HCl is a strong acid because every molecule of HCl that we put in solution will lose a hydrogen. So if I take an HCl and I put it in water, the probability that it loses a hydrogen is 100%. if I take CH3COOH and I put it in water, the probability that it loses a hydrogen is only 1%. So it has nothing to do with the fact that acetic acid has that CH3. It has nothing to do with the fact that it has those 3 hydrogens that it will never lose. It has to do with what is the probability that the hydrogen that it can lose, so that at that OH at the end, what's the probability that that will be lost? So if you're thinking about pH, what is, for each CH3COOH molecule that we put in water, how many H3O plus ions will we get? If I put 100 HCl molecules in water, then I will get 100 H3O plus ions. Whereas if I put 100 acetic acid CH3COOH molecules in water, I'll only get 1 H3O plus. So yeah, it has nothing to do with sort of the rest of the structure. It has to do with the probability that I will lose a hydrogen if I'm in solution. And yeah, I mean, the chemical reactions vary in the sense that, what that ion is will vary. So for HCl, the anion is Cl minus, whereas for CH3COOH, the anion is CH3COO minus. But really what's varying there is sort of the probability that this reaction is happening. So if you remember, we talked about reactions going forward and backwards. The HCl plus H2O reaction is going to go all the way to the H3O plus Cl products, whereas the CH3COOH reaction is not. So really what we're thinking about is what is our concentration of H3O plus. So the way that we measure that concentration is in molarity, which I think we talked about yesterday. So molarity of H3O plus is defined as the moles of H3O plus per liter of our solution. And we denote molarity using brackets. So brackets around H3O plus means molarity of H3O plus. So there's a question about how to determine whether CH3COOH will lose the hydrogen, and that's pretty hard. So it can depend what solvent you put it in, for example, so we don't only have to use water. But really that's something that you would have to be told in a given situation, or using tables and stuff like that. It's not always easy, especially with what we've learned so far, to predict. It's not randomized, it is sort of a property of how strong these bonds are, but that doesn't mean it's easy to just look at a molecule and know, with what we've learned so far. So just a math definition before we go farther into pH. So the definition of a log, in this case log base 10, is that the log of 10 to the a, where a is just some number, equals a. So the log of 100 is 2, because 100 is 10 to the 2. The log of 1,000 is 3, etc. So I think you've probably seen that in your math classes, but just as a reminder. So the definition of pH is -1 times the log of the H3O plus concentration. So what that means is that if my H3O plus concentration is 10 to the minus 3 molar, so 10 to the minus 3 moles per liter, that my pH will be 3. So the log of 10 to the minus 3 is minus 3, and then I'm doing -1 times that. So just, we have characterized the pH of a whole variety of solutions, and pure water has a pH of 7. So that means that if I take pure water I will have an H3O plus concentration of 10 to the minus 7 molar. So basically what's happening in water is that some small fraction of our water molecules are splitting into H plus and OH minus and combining and ending up with H3O plus. And then our acidic solutions have pH below 7, so they might have a H3O plus concentration of 10 to the minus 1 through 10 to the minus 7. So that's a little confusing because you would think intuitively maybe there's more H3O plus, so the pH should be higher. But what you have to remember is that 10 to the minus 1 is bigger than 10 to the minus 5. So 10 to the minus 1 is a higher concentration of H3O plus than 10 to the minus 5, so the pH is lower. And then basic solutions are the opposite, so they have a lower H3O plus concentration than pure water does. So just as practice, HBr is a strong acid. So what that means is that every molecule of HBr will split up into, will interact with water and become H3O plus and Cl minus. So I make an HBr solution that's 10 to the minus 5 molar. What is its pH? So I'm going to give you a couple minutes to talk about that in your breakout rooms and think about what you think the pH will be. As always, ask questions in the chat. Okay, let's just take 30 seconds to come back together. Okay, so the first thing we need to realize here is that because HBr is a strong acid, every molecule of HBr will undergo this reaction where it reacts with water to form H3O plus and Cl minus. And so that means that my H3O plus concentration will also be 10 to the minus 5. And so therefore, my pH, by the definition of pH, will be 5. So just to say that again, I put 10 to the minus 5 moles per liter of HBr in my solution. Then because HBr is a strong acid, all 10 to the minus 5 moles become H3O plus. So then my H3O plus concentration is 10 to the minus 5 molar, and then I use the definition of pH. So the log of 10 to the minus 5 is minus 5, and then minus 1 times that will be 5. So let me know if you have any questions in the chat. Okay, so if we combine an acid and a base, we can have what's called a neutralization reaction. So typically what that will look like is we have an acid and a base, and we make a salt and water. So as an example, if I have HNO3, that's an acid, it can lose its H in front of the NO3 and end up with an NO3 minus ion. And then rubidium hydroxide, RbOH, is a base. So a lot of bases end in OH. And the reason is that that OH can pop off and steal an H plus and be protonated. So the neutralization reaction will be HNO3 plus RbOH goes to RbNO3. So I'm combining sort of the Rb cation and the NO3 anion, and I'm making water with the proton that I stole from HNO3 and the OH that I stole from RbOH. So that is an example of a neutralization reaction. It's not that different from some of the reactions that you learned about yesterday, where you kind of just, each thing has like a cation and an anion, and so you just recombine them. So there's really only one way that you can recombine them here. If you split up your H and your NO3, either your H is going to go back with your NO3, in which case there's no reaction, or your H is going to go with the other anion, which is OH minus. And then that leaves your Rb and your NO3 to bond together. So our salt is RbNO3, and we've made water, which is H2O. So as practice in your groups, HCl is an acid and Li2O is a base. So talk together in your groups about how you would write your neutralization reaction. Do people feel like they need more time, or can we come back together in about 30 seconds to a minute? Okay, a little more time, so I'll give you about a minute or two from now. So let's come together at like 11:10, 11:11. Okay, let's come back together in about 30 seconds. Okay, so we're going to have HCl plus Li2O, our acid and our base. Those are the only two reactants that we have available, so the reactant side should be pretty easy. And then we're just going to recombine our Li and our Cl will become salt, so LiCl, and then our hydrogen and oxygen come together to form water. Hopefully you see this reaction and you notice that it is unbalanced and sort of get in the habit of always just pausing after you see an unbalanced reaction and fixing it. So in this case, we have 2 lithiums on our reactant side and only 1 on our product side. So we need to put a 2 in front of our lithium. And then to balance our chlorines and our hydrogens, we need to put a 2 in front of our HCl. So this is our neutralization reaction for HCl and Li2O, which is lithium oxide. So another characteristic of neutralization reactions is what's called the stoichiometric point. So you can think of that pretty simply as when the reactants are present in a stoichiometric ratio. So if you remember from a couple days ago, we talked about stoichiometry and limiting and excess reactants. So there's a question about what happened to the subscript of lithium. So we used to have 2 lithiums bound to 1 oxygen. So that was Li2O. But when we rearrange this and we end up with LiCl, lithium is going to have a +1 charge and chlorine is going to have a -1 charge. So we can only have 1 lithium to 1 chlorine. So that's why we needed the stoichiometric coefficient of 2 in front of LiCl, because we had 2 lithium atoms in our Li2O molecule, but only 1 lithium atom in 1 LiCl molecule. So we need that stoichiometric coefficient to make sure that there are 2 lithium atoms on each side. So where that comes from is that oxygen wants to have an oxidation number of -2, and lithium wants to have an oxidation number of +1. So we want 2 lithium atoms per oxygen. But chlorine is going to have an oxidation number of -1, or a charge of -1, and so it only wants to bond with 1 lithium, which has a charge of +1. Okay, so our stoichiometric point will be when our reactants are present in a stoichiometric ratio. So that is equivalent to neither of them are in excess. So looking at our first reaction, we have a stoichiometric coefficient of 1 in front of HNO3 and RBOH. So our stoichiometric point will be when we have a ratio of 1 mole of HNO3 to 1 mole of RBOH. So if I told you that I had 5 moles of HNO3 and asked you how much RBOH do I need to add in order to reach my stoichiometric point, the answer would be 5 moles, because then we'll have a ratio of 5 to 5 or 1 to 1. But then with our second reaction, we have different stoichiometric coefficients. So we have a 2 in front of our HCl and a 1 in front of our Li2O. So if I asked you, if I told you I have 10 moles of HCl, how many moles of Li2O do I need to add to reach the stoichiometric point? The answer would be 5. So I want to have a stoichiometric ratio of 2 to 1. So I have 10 moles of HCl, I need 5 moles of Li2O to reach my stoichiometric point. So this is kind of analogous to a lot of what you guys did on day 7 and problem set 7 with talking about limiting and excess reactants. Except what we're asking here is how much do we need to add so that neither of them is in excess? So I'm going to pause if anyone has any questions about neutralization reactions or stoichiometric point. Okay, if any more questions come up, please do put them in the chat as always. So we can use this stoichiometric point to do something that's called titration. So I guarantee that this, if you do the lab part of Chem 1A, that this will be one of the labs. I didn't check the syllabus, but I am confident that at some point someone will make you do titration. So the basis of titration is that I have, let's say, an acid solution of unknown concentration. That is called the analyte. That is what I'm trying to analyze to find its concentration. I can add a dye. Phenolphthalein is one common choice. Don't memorize that word, but that's just one of the common dyes that we associate with titration. And that dye turns pink when we reach the stoichiometric point. So it's clear in acids, and then as soon as we hit the stoichiometric point, it turns pink. So what I do is I add a base of known concentration. I keep track of how much of that base I've added, and I stop when the solution turns pink. So that base that I'm adding is called the titrant. So what that setup looks like is something like this. I have my flask with my acid solution that I've added my dye to. That's the thing on the bottom. I don't know its concentration. And then at the top, I'm slowly, drip by drip, adding base. And I can tell how much I've added. And then I stop adding more when the solution turns pink. So then I know how much base I've added at the point that the solution turns pink, which is the stoichiometric point. So basically what I'm going to be trying to do is I want to figure out what my initial concentration was based on how much titrant I need to add in order to reach the stoichiometric point. So I'll have an example of that, of how to do those types of calculations on the next slide. I just want to note that we can do the exact same thing for bases by adding an acid. So you would just switch, I have a base of unknown concentration and I'm adding an acid and waiting until the solution changes colors. And there are different dyes you can use depending on like what combinations of analytes and titrants you're wanting to use. Phenolphthalein is a really common one, but there are others. Does anyone have any like conceptual questions about what we are trying to do with titration? We'll go over the math of like how to actually do it on the next slide. Okay, so as an example, I have 50 milliliters of a solution of HCl. I know that it's HCl in water. I don't know the concentration of HCl. I add an NaOH solution that I know has a concentration of 0.5 molar. The solution is neutralized, which means it turns pink, after I've added 25 milliliters of that NaOH solution that is 0.5 molar. And what I want to know is what was my initial HCl concentration. So my first step will always be to write and balance the neutralization reaction. I can't know anything about the stoichiometric point without knowing the stoichiometric coefficients of my neutralization reaction. So in this case, my neutralization reaction is pretty simple. I have HCl plus NaOH, and it's going to go to NaCl, so that's the salt, plus water. This is already balanced. There's one Na, one Cl, 2 hydrogens, and 1 oxygen on each side. So all of my stoichiometric coefficients are 1. But I have to check that every time. So now I can calculate how many moles of NaOH did I add. So I'm just going to use the definition of molarity. So I have 25 milliliters of solution. That's how many milliliters of solution I added. And then I know my molarity is 0.5 moles of NaOH per liter, where 1 liter is 1,000 milliliters. So if I just do that math, 25 times 0.5 divided by 1,000, that means that I added 0.0125 moles of NaOH. So I know that that's how many moles I added to get to my stoichiometric point, and I know that my stoichiometric point has a ratio of 1:1 of HCl to NaOH. So I can use that to figure out how many moles of HCl there were. So I added 0.0125 moles of NaOH. Based on my stoichiometric coefficients, I need 1 mole of HCl per mole of NaOH at the stoichiometric point. So that means I had 0.0125 moles of HCl. And then the last thing I need to do is figure out what my initial HCl concentration was. So I know that I have 0.0125 moles of HCl. That's what I just figured out. I know that my initial volume was 50 milliliters. And then there's 1,000 milliliters per liter. So that gets me, if I just multiply through, that gets me 0.25 molar. So that is the initial concentration of my HCl solution that I figured out by doing a titration. So I'm going to have you in your groups solve an example a lot like this on the next slide. So if you have any questions about what I just did, now is the time. Okay, I don't see any questions, but if any more come up, please let me know. So the example I want you to practice with in your groups is a very similar concept. So I have 20 milliliters of an HBr solution of unknown concentration. I add calcium hydroxide, so CaOH2, and I know that that solution that I'm adding has a concentration of 0.1 molar. The solution is neutralized after I've added 15 milliliters of that. That should say CaOH2, sorry, that's a typo. So I've added 15 milliliters of my CaOH2 solution. What was my initial HCl concentration? HBr concentration. I made a copy-paste error. So just to reread that last line, the solution is neutralized after I've added 15 milliliters of my CaOH2 solution. And so what was my initial HBr concentration? So go ahead and work on that together in your groups, and let me know if you have any questions. I'll give you a little while to work on that. Yeah. Sorry, I cannot edit my typo live. It's very sad. So I've added 15 milliliters of CaOH2, and I want to know my initial HBr concentration.
Do you want to type in the chat with the typo?
Okay, does like 1 or 2 more minutes feel like enough time, or do you want more time? Okay, let's come back together at like 11:33. So that's about 3 more minutes, and then I'll go through the solutions. Okay, so just about 1 more minute. If you're not totally done, that's fine. Okay, let's just take 10 seconds to finish your thought and come back together. Okay, so the first thing that we always need to do is write and balance our reaction. So we're going to have HBr plus CaOH2 going to CaBr2 plus H2O. We have to be really careful about balancing here. So right now we have 2 bromines on the right and only 1 on the left. So we need to put a 2 in front of our HBr and then a 2 in front of our H2O. And if you didn't remember to do that this time, that's fine. You still got good practice with the rest of it, but just be aware that that throws your answer off by a factor of 2. Because instead of having a 2-to-1 ratio of HBr to CaOH2, you would solve it to have a 1-to-1 ratio. So not remembering to balance these equations can really have a big effect on your answer. So now I need to figure out how many moles of CaOH2 I added. So I added 15 milliliters of that solution, which I know is at a concentration of 0.1 molar, which means that I have 0.1 moles of CaOH2 to 1,000 milliliters of solution. So that means that I have 0.0015 moles of CaOH2. So there's a question about adding a subscript to Br. So the reason that I did that is if you think back to one of the earlier days where we talked about valence electrons, I know that my calcium wants to have a 2+ charge, and my bromine wants to have a -1 charge. So don't think about it as like adding a subscript to Br. Think about it as like, I know I want to make salt that has calcium as its cation and bromine as its anion. In what ratio do they need to be? So I think there were questions like this towards the end of, I want to say, problem set 3, maybe 4. So if you look at your valence electrons, calcium has 2 valence electrons and wants to lose those 2 valence electrons, so it's going to have a +2 charge. Bromine has 7 valence electrons. It wants to add 1 more, so that means it's going to want to have a -1 charge. So you definitely can't add subscripts in like HBr and CaOH2 because you'd be changing the compounds. But when you're trying to make salt out of calcium and bromide, they're going to need to have that subscript in order for the charges to work out. So let me know if that doesn't make sense, but yeah, so Ca is +2, bromine is -1, so we're going to need to have CaBr2 as our salt because of those charges. Follow up if you have more questions on that. So if I want to know how many moles of CaOH2 did I add, I have 15 mils of solution, that's milliliters, that's how many I added. And then I know that my molarity is 0.1 moles of CaOH2 per liter or per 1,000 milliliters of solution. So that means that I added 0.0015 moles of CaOH2. So now I use my stoichiometry and I need to figure out how many moles of HBr there initially were. So I know that I added 0.0015 moles of CaOH2, and then I know that my stoichiometric coefficients tell me that at the stoichiometric point, I have 2 moles of HBr per mole of CaOH2. So 0.0015 times 2 is 0.003. So that means that we initially had, or we always have, 0.003 moles of HBr. So then I can figure out my initial HBr concentration. So sorry, more typos. So I want to know my initial HBr concentration. So I had 0.003 moles of HBr, and initially I had a 20 milliliter solution. So that means that I have 0.003 divided by 20, and then times that 1,000 conversion factor between milliliters and liters to a 0.15 molar HBr solution. So that is basically how we practice using titration. Does anyone have any further questions on what I did here? So that brings us to kind of the end of the things that we think that you'll be expected to have had experience with before when you get into Chem 1A. So we've gone over kind of the things that we think are the most important. And yeah, there's a question in the chat. It's always that 1,000 mils is just me converting from milliliters to liters. So I'm going to go back to the beginning here. So just to go through this one last time, so I have so the way that titration works is that I have an acid of unknown concentration. I have a dye that will tell us when we reach the stoichiometric point. And I add a base of unknown concentration. And based on how much of that titrant, how much of that base I need to add in order to reach the stoichiometric point, I can figure out my initial concentration. And we can do this vice versa with acids versus bases. So the product of the neutralization reaction is just going to be salt and water. So for this example, I'll do the example that you just practiced with. So first I'm going to write my neutralization reaction. So I have HBr plus CaOH2 going to CaBr2, where I get those subscripts by the charge, those valence electrons, like we talked about earlier, and then plus water. So when you're writing these neutralization reactions, you always have to make sure that the molecules you're making are possible. So CaBr is not real. That can't happen because Ca wants to be +2 and Br wants to be -1. So this is just like early on in the course when we asked you like what will be the composition of a compound made of Ca and Br, and you needed to use those valence electrons. And then we need to balance this reaction. So this goes off one of the questions in the chat. So because there's 2 bromines on the product, so we have that CaBr2, so that bromine has a subscript of 2. So there are 2 bromine atoms on the product side. So that means that we need to have 2 bromine atoms on the reactant side. So we put a 2 in front of our HBr. And we also need to put a 2 in front of our water in order to balance the hydrogens and the oxygens. And then I'm figuring out how many moles of CaOH2 I added. So I added 15 milliliters of solution, and then I know that solution's concentration, so I can figure out the number of moles I needed to add. So I'm using 1,000 milliliters in the denominator there because it's 0.1 moles per liter. That's the definition of molarity, and 1,000 milliliters are in 1 liter. So I can figure out how many moles of HBr there initially were using that stoichiometric coefficient. So I'm using a 2 in front of my HBr because at my stoichiometric point, I need 2 moles of HBr for every 1 mole of CaOH2. That's what my stoichiometric coefficients mean. So that means that I initially had 0.003 moles of HBr. So my initial HBr concentration, again, sorry for the typo, is 0.003 moles of HBr in 20 milliliters of solution. So that was given. I know how much initial solution I have. And then just to convert milliliters to liters in order to get my answer in molarity, I'm multiplying by 1,000 milliliters per liter. So that's just my conversion factor. And I'm ending up with an answer of 0.15 molar HBr solution. Okay, so just to really quick go through the things that we talked about so far. The first day we talked about mass, matter, phases, and properties. So that was like intensive, extensive, chemical, physical properties. On day 2, we talked about energy, we talked about unit conversions and significant figures. Unit conversions are super important. I would definitely make sure you're comfortable, not necessarily having like memorized all the unit conversions, but if I tell you, 1 mile is 1,600 meters and ask you how many meters 5 miles is, like you should be able to do those kinds of conversions. Day 3, we talked about a lot of things. So atoms, protons, neutrons, electrons, isotopes, the periodic table, valence electrons, and Lewis structures. So that was like a lot of things. So just as an example, this is xenon. It's a noble gas. It has 54 protons, so that's its atomic number. And then you can see mass number at the bottom. So that means the average of the various isotopes, which have slightly different numbers of neutrons, mean that on average, an atom of xenon has a mass of 131.3 atomic mass units. We can use the periodic table to figure out how many valence electrons something has just by the groups. So ignoring the transition metals, all of the main group elements, we can tell how many valence electrons they'll have. And we can draw that in a Lewis structure. So for example, xenon has 8, so we start with 1, 2, 3, 4. So we're putting one electron in each orbital before we put a second electron in the same orbital. And then we fill up the rest of the orbitals. So this would be the Lewis dot structure of xenon. And then we talked about covalent versus ionic bonds and how to read line drawings. So for example, for this molecule that I've drawn here, I've circled all the carbons. So there are 10 carbons. And then wherever a carbon doesn't have enough bonds, we add hydrogens. So there are 13 hydrogens plus that NH2 group. So there are a total of 15 hydrogens. Day 5, we talked about naming, molecular formulas, empirical formulas, and moles. So being able to work with moles is super important. Don't memorize all of those nomenclature rules, but just be aware that they're out there and that you can look up tables. So 1 mole is 6.022 times 10 to the 23rd molecules. And then we talked about reactions, catalysts, and stoichiometry. So being able to balance reactions using stoichiometry is super, super important. So if you need more practice with that, I definitely recommend making sure you're comfortable with that. And then day 7, we talked about limiting and excess reactants and yield. Day 8, we talked about redox reactions and oxidation numbers. So just as a reminder, oxidation is loss of electrons or an increase in oxidation number. If something is oxidized, it's giving up its electrons to something else, and so therefore it's the reducing agent. Day 9, so yesterday we talked about mixtures and compounds, solutions, molarity, precipitation, all of that. And then today we talked about acids, bases, and titration. So that is kind of the end of the things that we think they will expect you to have seen before and be familiar with. But next week, we're going to get into wave physics and spectroscopy. So that's where Chem 1A starts. And you're really not expected to already know this. So we expect this to be brand new for everyone. So don't panic if this is brand new for you. But we just wanted to start getting into this because Chem 1A will go through it pretty quickly. So we just want you to have seen some of this before, be a little bit comfortable with waves so that when you start in Chem 1A, you're starting off pretty comfortable already. Okay, so that is all I have for today. Please stick around after class. If you have any questions, Katie and I will be in the Zoom room for our office hours.